In this video, we'll look at lesson 11.1 on lines that intersect circles. The essential questions that we'll answer are how do you identify tangents, secants, and chords of circles, and how do you use properties of tangents to solve problems. A chord is a segment whose endpoints lie on a circle. And you can see in the picture right here that this is a chord. It's important to note that it has to be a segment. So in our picture right here, this segment AB is a chord. But if I look at part of this thing right here, CD is also a chord. So AB and CD are chords. Now, a secant is a lot like a chord, but instead of a segment, it's going to be a line that intersects a circle at 2 points. You can see in the picture here, we have our secant, and then in this picture here, the secant is the line CD. The notation is really important when you're labeling these. So notice that the chord CD, I used the segment symbol with just a line and no arrows. And then secant CD has the line with the double arrows. Next, we have a tangent, and a tangent is a line in the same plane as a circle that intersects the circle at exactly 1 point. You can see that in this picture, line L is a tangent. Notice how line L only touches the circle at 1 point. That point is point E, and E is what we call a point of tangency. So point of tangency is the point where the tangent and a circle intersect. In our first example, we're going to practice identifying lines and segments that intersect a circle. Now, the first two words are reviews from previous units. Radii are radiuses of the circle, and if we look carefully here, the radius just needs to go from the center of the circle to a point on the circle. So LK is a radius, it's a segment, as is LJ and LM. So there are 3 radii on our picture. Diameter has to be a chord that goes through the center of the circle. So KM here is a segment, KM is a diameter. And if you want to make note of that a diameter goes through the center of a circle, that would be good. Now, a diameter is a special type of chord because a diameter has 2 endpoints on the circle and it's a segment. So when I'm naming my chords, one of the chords will be the diameter KM. There's another chord that is not a diameter, and that goes from here to here, JM. Notice how JM does not go through the center of the circle, but it's still a segment whose endpoints are on the circle. So the first 3 things that we found, the radii, diameter, and chords, these are all segments. Secants and tangents are both lines. And the secant has to be a line that intersects the circle at 2 points. And you can see in the diagram here that that is line JM. Notice I used the line symbol with the double arrowhead. Then a tangent line intersects the circle at just 1 point. And if we look carefully, we can see that that is this line right here. Notice there's a lowercase m that is indicating the line. We can either just say M, or you could call it line M. Either way, those are the same thing. For the try now example, you're going to do the reverse of what we just did in example 1. It gives you the name of the segment or line, and you're going to classify it as either a radius, chord, diameter, secant, or tangent. It's possible that something might be more than one of those. Please pause the video now and give that a try. Here are your solutions to the try now. Anytime you have a diameter is always a chord. The others are just one thing: secant, tangent, and radius. Next, let's talk about some vocabulary related to pairs of circles. Congruent circles are two circles that have congruent radii. So the definition here, you can see it's written as a biconditional. Two circles are congruent if and only if they have congruent radii. That means it goes both ways. So if I wanted to write the biconditional for the picture right here, I could say something like circle A is congruent to circle B if and only if the radii AC is congruent to BD. So congruent radii, same length, that's what makes circles congruent. Concentric circles are coplanar circles with the same center. So here our circles have the same center, but different radii. If the radii were the same and the center was the same, then the circles would really just be the exact same. They'd be right on top of each other. So concentric circles are going to be same center point, but different sizes. If you think of like a target or a dartboard, those are all concentric circles. Next up, we have tangent circles. And just like a tangent line on a circle, tangent circles are going to be circles that intersect at exactly one point. You can see in the picture that the circles on the left and the circles on the right both intersect each other at just one point. The circles on the left there are called internally tangent circles. And the circles on the right, where they touch on their outsides, those are externally tangent circles. In this next example, we're going to look at tangent circles, and we're going to find the length of each radius, identify the point of tangency, and write the equation of the tangent line at this point. For the radius of each circle, you want to count either vertically or horizontally. So for example, in this first circle, I could choose this right here, and I can count 1, 2, 3, 4. So the radius of circle A is 4. Then for circle B, I can find again a segment, and here I will count horizontally. You just need to count horizontally or vertically so that you can count the boxes straight. So radius of circle B is 2. You can see that the point of tangency is right there. And when we name our point of tangency, we're going to list it as an ordered pair XY. So that point of tangency is the ordered pair 3, 0. And then for the equation of the tangent line, we want to come up with an equation for this line right here. And if you look carefully at this line, every single point on that line has an x value of 3. The y value can be whatever it wants to be. So the equation of a vertical line is going to be an x equal line. That's something that you would have learned in your algebra courses. Anytime we have a vertical line, it's x equal a constant. And if we have y equals a constant number, then it's a horizontal line, and we'll go from left to right. So using that information, go ahead and try the try now on your own. Please pause your video. Here is your solution. The point of tangency is the ordered pair 2, -1. And then because the tangent line is a horizontal line, it needs to be y equal because every point on this line has the same y value of -1. The x can be anything, but the y value has to equal -1. Here are a few theorems related to tangents of circles. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So in this picture, you can see that line L is tangent to circle A. We would then be able to make the conclusion that L is perpendicular to radius AB. So L is that tangent line, and AB is the radius at that point of tangency, point B. So that makes a 90-degree angle. The next theorem is really just the converse of the first theorem here. If a line is perpendicular to a radius of a circle at a point on a circle, then the line is tangent to the circle. So in our picture here, if M is perpendicular to CD at D, then M is tangent to circle C. Now let's look at an application of those theorems involving tangents of a circle. Here we have a space application. The International Space Station orbits Earth at an altitude of 240 miles. So in our picture here, the S is going to be the International Space Station. And then if it's orbiting at an altitude of 240 miles, that means it's orbiting 240 miles above the surface of the Earth. So that's 240 there. We're looking for the distance from the space station to the Earth's horizon to the nearest mile. And that is going to be this distance right here where there's the question mark. Now we're given that the radius of the Earth is 4,000 miles, and that's going to be key to help us solve the problem. So CH is 4,000 miles, and then since the radii are always congruent, we know that CD is also 4,000 miles. And now we have a right triangle that we formed with that tangent, and with a right triangle, we're able to apply our Pythagorean theorem, a squared plus b squared equals c squared. Notice that the x and the 4,000 are the a and the b, they're the legs. So x squared plus 4,000 squared equals, and then c is the hypotenuse, which is this full distance right there. So for that, you're going to need to add up the 4,000 plus 240, and that's 4,240. So that's going to be our c value for 240. And then you can actually do most of this in your calculator. So if you just subtract the 4,000 squared on each side, you can then type this expression into your calculator using the square button. And when you do that, you'll get x squared equals 1,977,600. Now to get the x, we just need to square root that value. And when you stick that into your calculator, you will end up with x equals 1,406.27. We'll round to the nearest mile, which is the nearest whole number. The 2 rounds down, so we're going to say it's about 1,406 miles to the horizon. This try now is very similar to the previous problem, but this time we have the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles early in its flight. And we want to know what's the distance from the spacecraft to Earth's horizon rounded to the nearest mile. If you'd like to try this problem, you can pause your video now, and then when you hit play again, the solution will be posted. Please pause. Okay, here is your solution to your try now. I drew a picture very similar to the one we drew in example 3, but the Apollo 11 was only 120 above the surface of the Earth, and then we do our Pythagorean theorem and solve and end up with about 987 miles. For our final example in this lesson, we're going to talk about what happens if two segments are tangent to a circle at the same external point. So in our diagram here, this point E is an external point because it's outside the circle. Theorem 11.1.3 states that if two segments are tangent to a circle from the same external point, then the segments are congruent. So if we know that they're both tangent to the circle at different points, we know that these two segments are congruent. So segment EF is congruent to segment EG. In these examples, the segments in the figure are all tangent to the circle, and we want to find the length. Because they're tangent to the circle and they meet at that common external point, we know that these two segments are equal to each other. So that 5y minus 28 has to be equal to 3y. And now we can use our algebra skills to solve. I'm going to subtract 3y on each side. So 2y minus 28 equals 0. Then we can add 28 on each side to get 2y equals 28. Divide by 2, and we end up with y equals 14. The question asks us to find, that should say df. And to find df, we can just plug in that 14 into this expression right there. So 3 times 14, and that is 42. So the length of segment df is 42 units. Now, if we were to calculate the length of DE, 5 times 14 minus 28, that would also equal 42. So both of them should be the same. You might want to just plug it into both and make sure that you get the same answer. That will tell you that you did your algebra correct. Here's one final example for you to try on your own. Pause the video and give this a try. All right, here is your solution. Algebraically, setting those equal to each other, you should come up with A equals 12. And then if we evaluate segment HG by plugging in the 12, you end up with HG equals 28. And this is our final problem of this lesson. So thanks for watching and good luck as you practice some circles on your own. Bye.